Good afternoon and welcome to Advanced NMR Spectroscopy course. So today I'll continue with spin-spin coupling. So this is lecture 8th lecture. So if you have any doubt about your earlier class or earlier classes, so you can we can discuss once I finish this lecture. Okay. So in the last class, I told about the coupling. Okay. So now I will see about the sign and magnitude of the coupling constant. Okay. So before that, what we will see that what we will do that how to use the quantum mechanics for this how quantum mechanics is applied to this coupling constant. Okay, so now these are the things I have already told you, that the energy of a spin state of value mi in an external magnetic field B0 is given by EI is equal to minus mi gamma B0 h by 2 pi. So that all of you know it is nothing but minus mi h nu. Okay, this is for a particular energy state where gamma is the gyromagnetic ratio and nu is the precessional frequency of the isotope under the applied magnetic field. Okay. Now we'll see that we'll try to analyze only one spin system and then we'll slowly go to two spin system. Okay. So in case of one spin system, there are two energy levels. We know that E half is equal to E alpha is equal to minus nu by 2 and E minus half is equal to E beta nu by 2. See, actually what we are doing, we are just omitting H because we know the nu is proportional to energy. So at any stage, because if you're just trying to simplify the mathematical relation so that it will look better. Okay, if you want to convert that to at any time into energy, you can just multiply the equations with Planck's constant. Okay. So where the alpha state is the upspin having lower energy and beta state is the downspin. Those are the things I have told you, and this is the selection rule for NMR, that it is delta M is equal to plus minus 1, where delta M is the MI value of the initial minus MI value of the final. Okay, so this tells that means at any time only one spin can flip up or down and down at one time. Okay, suppose if you are now in this particular, it is only one spin, so that will only flip. But when you will go for multiple spin, you will see that when we draw the energy diagram, we will see that only one spin at a time can flip. So in case of single spin, okay, so delta M is nothing but initial is plus half, the lower energy state minus the final is minus half, so that is 1. Okay, and the energy difference is nu alpha beta is E beta minus E alpha, and that is nothing but the nu or the resonance frequency. Now we'll analyze the two spins. So that was the for one spin, it was fine. Now we'll see what happens when you have two spins. Later, and we will consider the spins having both I value is equal to half. Okay, so two coupled spins with I is equal to half will give two doublets. Okay, so one due to each of these spins, and one will be centered at the delta A, one spin, and another will be centered, and the second spin is delta B. And in this particular case, we will specifically take that specifically we will choose that delta A, the chemical shift value of A is greater than delta B. Okay. And so what you will see that the spacing between the two lines in each doublet is same. That already in the last class I have discussed, that if JAB is equal to JBA, if A, the coupling constant between A and B will be always same. And this splitting is called scalar coupling, and its unit is Hertz. That also I have told in the last class. And this subscript indicates which spins are involved. Sometimes, so this is there are only two spin in this case, so we'll call this is a AB A and B, so it will be JAB. And sometimes we also put a superscript before J that indicates the number of bonds involved. But anyway, we are not concerned about here about the number of bonds. Okay. Okay, so the equation, so if you want to, so if you consider, let us say you have a, so we told that delta A is, so the delta A will be relative. So click karo. Okay, okay. So this is your delta A position and this is your delta B position. So what you will see a this is your, so you will see that this will be also a doublet with JAB and this will also be JBA and JBA equal to JAB. Okay, and now so I am trying to give you the how to so see when there is any this, so there are energy levels from where transitions are happening. Okay, so how to find out the energy levels for the each spin system when they are interacting. So I have given you a this in this particular case. This is EMA-MB. MA is the nuclear spin state of nuclei A. This is the spin state of the nuclei B, and then what will be the energy of that state is depends on the MA value, nu A value, M value of the B nuclei, nu value of the resonance frequency of B, and then this is the coupling constant. Okay, and the energy levels are given here. So now you can see there could be 4 energy levels, one due to both the spins are at the alpha state. In the second energy level will be one spin stated in alpha, another in beta. The third is the first one is beta and second one is alpha, and the fourth energy state are beta. Both are beta, and if you see that if you use this equation, okay, so if you see for the when they are both are alpha, so this is nothing but minus of nu A, because this in this case this is mi is equal to plus half, so it will be minus half nu A minus half nu B, and this is the coupling constant. Ma and mb is half into half JAB. So similarly, if in one case this is the first spin is alpha, so that's why the energy is minus half A, and second stated now beta, so beta is nothing but minus half, so this is minus half minus half, and then because one spin is plus half, another is minus half, so it is minus 1/4 JAB. So you can find out what will be the energy of all these 4 states. And I have given the total M values. If you remember, yesterday I was using this total M value summation of MI. Okay, we here only have 2 spins, so I have considered the M value of 2 spins. So in case of when both are in beta, it is -1. When both are in alpha, it is called they are in +1, and one here both the cases it is 0 because one is alpha, another is beta. But say let us say you have more than 2 spins, so then in that case what you have to do is that EMI-MJ, okay, because always your coupling will be at a time we will be considering a coupling with a second nuclei, second spin. So EMI-MJ is equal to summation of minus MI nu I plus this MI-MJ JI, where I is not equal to J. Okay. So if it is a 3 spin, you can find out what should be the, if you have a 3 spins, there will be 8 energy levels, and then how you will do it. Okay, that I have already, you can yourself try, otherwise if it is required, I'll discuss it again later. Okay, so for homonuclear case, okay, so nu and nu B are very close because they both of them are the proton. Okay, homonuclear means we are considering here proton, so they are very close frequency. But if you consider this nu A or nu B, they are much greater than coupling constant, because nu is in megahertz. If you see this, the resonance frequency of the nucleus is in megahertz, where J is in hertz. Okay. Same thing I have shown you in a diagram. So now if you see that this is your alpha alpha state, this is your alpha beta state, this is beta alpha, this is beta beta. So this is the case when you have the homonuclear. Okay, that's why alpha beta and beta alpha states are very, energies are comparable. But if you later consider one is carbon 13 and another is hydrogen, then you will see that this alpha beta, so this is, let us say this is alpha for carbon 13, this is beta for carbon 13, because that is having lower energy. We know the effect, because the gyromagnetic ratio of carbon 13 is much less, 1/4 of proton, so that affects the energy level. So that's why this energy level is much lower. And then if you see that in this case the carbon is in alpha state but proton in beta, so this is the or higher energy state of the proton, and now this is for both of them are for beta. Now if you see the considering, if you remember our selection rule, only at a time only one spin flipping is allowed. So in this case, see in this blue line, you see that the first spin is remain intact, only the second spin is changing its spin. Okay. Similarly, from 3 to 4, the first spin, the beta is not changing, only the alpha is changing. Similarly, from 1 to 3, it is the first spin is changing, whereas the second spin remain constant. Okay. And from 2 to 4 also, the second remain constant, the first spin changes. So these two red lines corresponds to change in the spin state of first, and these two blue line is the corresponds to the change of spin of the second spin, and same thing for here. So that's why that these two diagrams show that these two alpha beta state and beta alpha states are of very similar comparable energy when they are homonuclear. But if you consider for heteronuclear, like you consider for proton carbon or proton fluorine or proton phosphorus, then the alpha beta and beta alpha are not same. That is the reason I am showing it here. And of course we will be mostly considering here the homonuclear state. Okay. So again I have shown you the energy levels of this state 1, state 2, state 3 and state 4, which I have shown you earlier. I have tabulated this thing, so you can again see that this is the so resonance coming from the resonance frequency of A, this is coming from the resonance frequency of B, and this is from the mi value of A and B, and both are alpha now, so both are plus up, so this is positive. And you can see this is alpha beta, and both one is alpha beta, another is, so this is always negative, this is also negative, because one is plus, another is minus. Similarly here one spin has changed, so this spin has changed, here this spin has changed. Okay. So and here you can see both of them have changed. Okay. And okay. So now I have defined the spins, the corresponding transitions and their energies. Okay. So now let us see that what happens when the coupling. Now I told you the coupling constant. Okay. Coupling constant can have both, it can be positive value, it can be negative value. We will see for which type of coupling it will be positive, which type of coupling it will be negative. We will see today's lecture later on. But let us consider that when JAB is positive. Okay. So when JAB is positive, this line number 1 to 2. Okay. So it will be 2 minus 1. So that only I have done here mathematically. E2, this is the E2 minus E1, that only I have shown it here. If you see that ultimately you get this nu B minus half JAB. So this is nothing but the precessional frequency of the nucleus B minus half of coupling constant of JAB. Similarly nu 3 4, because these two are from the transition of B nuclei. So again this will be nu B nuclei, and this is plus JAB. Now when JAB is negative, what happens to when this JAB is negative? It is nothing, only there is a change in the, now because now JAB, this is the absolute value of J. Okay. So now as JAB is negative, okay, so this will be the equation, if you put all those things, it becomes like this. Similarly, line 3, 4 will be nu V minus half J AB. So this is the mod value of J. So absolute value of J. Okay. Now let us see how. So now let us see that. So what we have seen here is, let us say, spin 1 to 2. So 1 to 2. So what happens? The spin B is changing. Spin B is changing. Okay, spin A is remain constant. So this is a spin state alpha alpha to alpha beta, and we have seen that when JAB is positive, it will be nu B minus. So this is your nu B. Okay, so 1 to line will be. So this is your nu B. So it is minus JAB. So you see, that's why the line is this side. So this is your nu B position. Okay, this central line. So it is minus JAB, and you see the second line is plus J plus. Okay, so second line is plus. Okay. Now you see that line 1 to 3, 1 to 3, spin A is changing, B remains intact. Okay, so it is alpha alpha to beta alpha, and again you can see that this is your line 1 3. This is your the chemical seed position. This is minus, and this is plus. So always remember that the frequency is left hand side, it is plus. Okay, so when you have JAB is positive, your 1 2 line is uphill, 3 4 line is downhill. In case of nu B, in case of nu A, 1 3 line is uphill, 2 4 line is downhill. Now see, when JAB is negative, what happens? Exactly, it's just nothing. You get the same spectrum, but the line, the transitions, so the origin of these lines are different. So now, which was coming at downhill is now moved to uphill. Okay, but you will not visibly any change in the spectrum. Okay, you only see the appearance of spectrum is same. So there is no difference when whether it is JAB is positive or negative. But actually, if you read very carefully, there is a change in the transition. From which transition the lines are coming will be now interchanged. Okay, so same thing, only I have drawn it here. Okay, so what it tells that each allowed transition corresponds to one of the spins flipping from one spin to other, while the spin state of the other spin remains fixed. That I told, at any time only one spin is changing. Okay, so that I have already explained to you. The lines of a multiplier can be associated with different spin state of the coupled spins. Okay, when J is negative, that I told, it only swaps over, is the spin state of the passive spin associated with each line of the multiplier. Okay, so the lines are only just getting swapped, nothing else. So the overall appearance of the spectrum is therefore independent of the sign of the coupling constant. Okay. Now let us see what are the factors which affecting the sign of J. Okay, so first thing is that the scalar coupling. We already told you that J is called scalar coupling also. The scalar coupling of one nuclei with another takes place through the intervening bonding electrons. Okay, this is very important. Okay, so there will be another coupling. We will see that nucleus are coupling, interacting with another nuclei through space. Okay, that we will see later on. So this is called scalar coupling because it interacts through the intervening electrons. So that's why the magnitude of J thus decreases as the number of intervening bonds decreases. Okay, so as the number of bond you are putting increasing. That's why I told, if you remember in my that last class, that I have told that mostly you see the coupling constant up to 3 bond. Beyond 3 bond, there are very rare cases. We will see today some examples where you can see the coupling. But normally 3 bond distance is common, but you can see up to 4 5 bonds like aromatic compounds or double bond containing compounds or acyclic containing compounds. Okay, so most cases I told you it is limited up to 3 bonds. Arisco Latin. Okay, so now you see that a chemical bond consists of an electron pair that all of you know, with opposite signs. This is very important. Okay, in a bond, always the electron pair will have opposite signs. So that the spins are paired in and they are in a molecular orbital, and that is governed by Pauli's exclusion principle. So they are antiparallel. Okay, so this is one point you must remember. Next is the like bonding electron pair. The preferred orientation of a nuclear spin is opposite to that of the nearby sorry. Sorry. So the bonding electron, so like bonding electron pair, you will see when there is a nucleus will also try to pair with the bonding electron, nearby electron, it will like to pair. Okay, we will show you in the diagram. Similarly, when two nuclei are connected through one bond distance, okay, when they are connected through one bond distance, they will also prefer to be antiparallel. Okay, and that is the most stabilized configuration. So you can see here, this is the bond, these blue are the electrons, they are coming from this is the molecular orbital, they are coming from, these are the electrons, and you see they prefer to be paired. Okay, so automatically the nucleus adjacent to this is also preferred to be antiparallel with this electron. Similarly, this is the other nucleus which is now antiparallel, and when these two becoming antiparallel, now these two nuclei are also becoming antiparallel. So when the two nuclei are connected through one bond, the antiparallel is the most preferred configuration. Okay, and that is the lower energy, whereas you can draw a parallel. See, this will remain always anti-parallel, the bonding electron pairs in a bond, but the nuclear, they can be parallel also. Okay, that is a higher energy configuration. So you remember that when two nuclei are connected through one bond, the preferred orientation will be anti-parallel, that will have stabilized in energy. Okay. So this is, I have explained you in case of when J is when gyromagnetic ratio is positive. Okay. Okay. So when the gyromagnetic ratio is positive, you will see a J is positive. But if gyromagnetic ratio is negative, you will see J will be negative, because gyromagnetic ratio is also important parameter in calculation of the sign of the J value. We will see that. Now let us see when the two nuclei are separated by two bonds. Okay, you can see, let us say you have a CH2. Okay, so you have a molecular orbital carbon, let us say whether it is a sp2, sp3, sp does not matter for you, and at least there should be two or either it could be sp3 or sp2. So you see that electron will be always paired. Okay, and you can think that one nucleus will be pairing with one of the electron. Now let's see this one. Now this configuration, so this is one molecular orbital, this is another molecular orbital. So here also this, if you consider the molecular orbital, that will be paired, but if you consider these two electrons, they will prefer to be parallel. That is governed by the Hund's rule. Okay, with maximum multiplicity. Okay, so that also you know. So this will be the preferred arrangement of electron in the two MOs, and automatically if you consider one of these nuclei will prefer to be antiparallel, but here if you consider the antiparallel with the electron, then you will see that both the nucleus are in parallel. So when for a two bond case, you will see the configuration with two parallel nuclei is having lower energy compared to the two nuclei are anti-parallel. Okay, clear? So so in this case, the J is negative when two nuclei are anti-parallel, they are negative. Okay. Now, I have summarized all those things in this energy diagram. Okay, so try to understand it very carefully. Now, let us consider you have two spins alpha A and alpha B. Okay, so sorry, two spin alpha, sorry, A and B. So the four energy states are alpha A, alpha B. This is, I have shown the alpha A, beta B slightly lower in energy, and then beta A, alpha B slightly higher in energy, and this is the beta beta. Okay, so when there is no coupling, okay, so you will see that this is due to the change of the spin of the A. This is due to the change, these two are the due to the change of the spin of A, and these two are the change of the spin of B. And you see this requires higher energy, that's why the delta A value is higher frequency, where delta B is lower frequency. Okay, now let us say when they are connected, okay, now there is a interaction. Okay, so one interaction is that I told you that when the anti-parallel state is having lower energy, okay, where you have seen that, when you have seen the scene that you have seen when they are connected through one bond, we have seen that this is lowering energy, and parallel state are having higher energy. So in this case the J is positive, and you see now, so now you see that delta B is coming from line 1, 2 and 3, 4. Delta A is coming from line 1, 3 and line 2, 4. Okay, so now if you see the same thing, when there are two nuclei are connected through two bonds, you will see that 2J, this is negative, because if you see the now the parallel state is having lower energy. Okay, the parallel state is having lower energy, whereas in case of 1J case the parallel state was having higher energy. Okay, so that's why in this case the J is negative, because it is now coming down. So this is the J is negative, that's why the energy it is coming down. If you see the equation, if you see the equation, you will see that only when J become negative, then this can come down. Okay, so that's why in 2J case this is negative, so that's why the 3, 4 lines comes first, then 1, 2 lines, and then here also 2, 4 lines, the transition between 2 and 4 comes first, and then the transition 1, 3 is having the highest energy. And this is the, you see the parallel case, the parallel is more stabilized, that's why the parallel is shown here, and if you do put that parallel, then you will see that JAB is negative. Okay, so you will see quite general that odd number of, I have shown for 1 and 2, odd number of intervening bonds gives a positive J value, while even number of intervening bonds give J value is negative. This is very important. You will see that when you go for 3 bond or so, now you will see that, but it is not hard and fast. You will see many cases there are substituent effects. Okay, so you will see that there, and sometimes depending on the nuclei, let us say in case of fluorine, okay, fluorine is having I value is plus half, or gyromagnetic ratio is positive. Still in many cases you will see that fluorine couplings are showing a different sign, because fluorine, beside this, fluorine is also having lone pairs. You have the bonding pairs, but it is also having lone pairs, so those also affect the spin of the nucleus. Okay, so there are, that's what I'm telling, there are many, see, so many, everything cannot be taught in the class, but you must remember that it is more or less commonly seen case of hydrogen, but there are exceptions also. Okay, now let us see what are the different factors that influence the magnitude of J. You will see the absolute value of J depends on the gyromagnetic ratio of the two interacting nuclei, like the absolute value depends on the gyromagnetic ratio of the two interacting nuclei. Then Fa, I'll tell what is Fa, what is Fb and F. Okay, so this F is nothing, it is a fraction of s orbital character of the atomic orbital used to create the MO. Okay, like let us say sp3. In sp3 you will see the fraction of s orbital is less than sp2 than sp. Okay, so s orbital character in the molecular orbital is very important. If it is more, you will see that JAB value increases. Okay, so that in case of so let us say a CH bond, we know the hydrogen is giving full S only the carbon is using is sp2 or sp3 or sp. Okay, so it depends on the fraction of s character of the interacting atomic orbitals, and f is nothing, it is the angle. So we'll see there are various angles. There will be, you will see the bond angle, then you will see the dihedral angle. Okay, so that also depends on the angle. Okay, so angular dependence is represented by f. Okay, so thus all other things being equal, okay, if you keep all other things equal, the magnitude of J is proportional to the gyromagnetic ratio of the interacting nuclei. So if the gyromagnetic ratio are high, you will see the coupling constant is higher. For example, I will tell, let us say hydrogen coupling constant versus hydrogen deuterium. Okay, so you will see that hydrogen coupling constant is more than hydrogen deuterium, because deuterium gyromagnetic ratio is less. So since few elements have negative gyromagnetic ratio, coupling between nuclei with opposite sign will reverse the sign. That also you must remember. That's why I was telling, if you all our discussion so far, I told that it depends on the sign of the gyromagnetic ratio. But there are, as told, I told you, there are exceptions also. Okay. Now let us see what are the magnitude of one bond coupling constant. We know the one bond coupling constants. We can see in many systems like carbon hydrogen, carbon deuterium, carbon fluorine, carbon phosphorus hydrogen, like that. Okay, and we know that J is positive in these cases, as the antiparallel state have lower energy. That also I have explained you previously. So while bonding hydrogen, so you now see in the bonding, the hydrogen is using 1s orbital, but carbon is using different type of hydrogen like sp, that I have already explained to you. Okay, therefore 1JCH depends on the hybridization of the carbon orbital. Okay, so here I have shown that if you have sp-n hybrid, the s character to p character is 1:n, because n represent the p and 1 is for hydrogen, and any sp hybrid, so if s fraction of s and fraction of p should always equal to 1. So in general, so if you see that there is the equation, so 1JCH is equal to 500 into fraction of s character. Okay, this fs arch. Okay, let us say if you have you are bonding a CH. Okay, so let us say this is sp3. So what is fs? Fs is equal to 1 divided by 3 plus 1, so it is 1/4 or 0.25. So your 1JCH will be 500 into 0.25. If you change it to sp2, this will become now 3, so this will become 0.33. So for 1GCH, this is I will for write sp3, this will I write sp2 is equal to 500 into 0.33. Now if you consider a 1JCH sp hybridized, it will be 500 into 0.5. If you see fs of sp will be 1 divided by 1 plus 1 is equal to 1/2 is equal to 0.5. Okay, so you will see that as the s character increases, you will get the coupling constant value will be more. ओके सॉरी, इसको कैसे ये करने का इस इसको हटाने का कैसे, ये जो लिखा है बहुत टाइम लगेगा, ऐसा कभी कभी हो जाता है ना। नहीं नीचे का खाली मुझे कुछ है मैटर, ठीक है वो हो जाएगा, अभी उतना दिखेगा, उसको वो भी ग्रीन कलर में था ना, इसके लिए प्रॉब्लम। ओके so why this reason that why the s character actually increase the coupling constant? Because if you see from quantum mechanics, you have seen that s orbital electron has a finite probability at the nucleus than p orbital. Okay, because p orbital is having a nodal plane at the nucleus. Okay, whereas s orbital has a finite probability. So if the s that means that if you have a greater s character in the hybrid orbital, that will communicate nuclear spin information between neighboring nuclear more efficiently. That's why if the s character increases, that also increases. Okay, here CP Singh wants to know something, raised hand. Okay, Silpi, I'll discuss with you once the lecture is over. Okay, let me continue. Okay, okay, you can note down what is your doubt. So again, whatever I told in my previous slide have been summarized here. You can see sp3, sp2, and sp I have summarized here again, so I will not repeat it. And you see, as the hybridization s character increases, the coupling constant increase from 125 to 1 ch coupling 1 ch coupling constant 125, 156, and it is 249. So surely it depends on क्या हो गया. So I have here shown the one bond coupling constant. So some of you might be surprised to see a hydrogen coupling constant. Okay, how it has been found. I will let you know how this has been found out. Okay, one can find out, like even methane. If you consider the, let us say, methane, all hydrogens are coupling to each other. In a spectrum, we don't see that. I already told you. If you have the same resonance frequency, the couplings are present, but we don't see them. But how to find out? So you have to do it in an indirect way. So this coupling constant of like hydrogen coupling constant in hydrogen molecule has been found to be very large, 280 hertz. But if you record, you will not get 280 hertz. You will get only single line because both the hydrogens are equivalent. So I'll tell you how to find out, but you should remember that normally one bond coupling constants are quite large. You can see even 500 to 700 hertz. In many cases, if you see in case of fluorine and carbon 13 that I was telling you, okay, you see that this is both of gyromagnetic ratios are positive, both are of spin value half, but the values is negative, and that negative is coming due to the effect of the unshared pair of electron on the fluorine. Okay, it is not only the bonding pairs, but if your the spinning nucleus is having spinning atom is the NMR, the active atom is having a lone pair, that also affects. Okay, so that's why in some cases you will see, like in case of phosphorus coupling. Okay, now we'll go to the two-bond coupling constant. We call this as a geminal coupling constant. The magnitude is, of course, now there is one, you have added one more bond, so it will be a smaller, and I have already told you that it will be negative coupling constant. Okay, in case of 1 it was positive, 2 bond it is negative coupling constant, right? Because why I told that, because the parallel spins will have lower energy than the anti-parallel spin, and if you analyze that the energy diagram carefully, you will see that is the reason. Now, like one bond, this geminal coupling constant is also sensitive to gyromagnetic ratio. So that formula is applicable here also. Okay, S character also. Okay. And also the angle factor is coming now. See, when you have one bond, you do not have much. This is let us say A nuclear, B nuclear. There is no question of bond angle. Now let us say you have a hydrogen here, you have a hydrogen here. Okay, two bond. So this angle can be different depending on what molecule. If it is if the carbon is hybridization also is also important. Okay. So if it is sp2, the bond angle will be different. If it is sp3, it will be different. If it is a cyclic system, it will be different. If it is cyclopropane, it will be different. We'll see all those things. Okay, so it depends on that. That is this F factor will now be playing in case of two bond and beyond that. The two bond coupling constants are usually fall in the range of, you will see then of course they will become negative and they are less than the one bond because it is now far away. Normally the James CH2 group hydrogens are equivalent. Normally you will see many molecules CH2, CH2, CH2 they are equivalent, but they sometimes become non-equivalent when they are diastereotypic. If you remember yesterday I showed, like let us say valine. Okay, those two methyl groups, if you see the leucine like that. So CH2 groups which is next adjacent to the chiral center or even away from the chiral center, they become chemically non-equivalent and then they may couple to each other. Okay, so these are the standard coupling constants I have shown for two bond coupling constant. This is for your methane. If you see the methane coupling constant is minus 12.4. You may ask how, we will tell you how to find out. Now if you see in cyclic case, okay, in cycloalkanes you can see that when for cyclopropane this value is minus 4.3, and now as you increasing the ring size, the negative sign is increasing. Okay, so that means if you are ring that, now in case of cyclopropane there are two factors. One is the, if you see the cyclopropane system, you have a different kind of bonding, and also the cyclopropane system the bond angles are different. You see this in this case, so the value is now become slightly positive. Okay, so that depends on, see now if you're, see when your S character increases, the coupling constant J value increases. Okay, so J value was negative, let us say negative 5, so it is increasing, so automatically this value will not be minus 7. Okay, it will be rather minus 2, or even it can become plus 2. So that is the case. That's why in case of ethylene these values become plus 2 because of the more S character in the orbitals or the participating orbital, okay, from the carbon, because it is sp2. Okay, so similarly I cannot want to explain all, but there will be some cases that there will be slightly positive value. You see in case now fluorine, now it has become positive. So wherever there is a fluorine, it is not that the gyromagnetic ratio is negative, it is due to the lone pair of that. Okay, in this case also, see fluorine coupling constant here, carbon fluorine coupling constant or fluorine coupling constant, they are positive, although they are supposed to be negative. Now the question was that how to find out the when the protons are equivalent, how can you find out the coupling constant? So what you have to do, that you replace one of the hydrogen, okay, with deuterium, and then measure the JHD. Okay. Now there will be a coupling. Okay. So now if you remember that if I have told you that if all other things remain constant, the coupling constant value depends on the gyromagnetic ratio of the two nuclei. Because other things are, because hydrogen and deuterium, they have the, so all other same things will be same, except that these two values. Okay, so similarly, so JHD is equal to constant to this, JH is equal to constant to this. So now the ratio of the gyromagnetic ratio of deuterium by hydrogen. Now these all you know the JHD is known, gamma gyromagnetic ratio of hydrogen is known, gyromagnetic ratio of deuterium is known. So if you can experimentally or by NMR you find out the JHD, you can actually calculate. So that is those are the values I showed you. Those are not directly measured. You cannot measure the direct coupling constant of methane or hydrogen. This is the way it is being done. Okay. Now two bond. So now I told you the effect of hybridization. As the going from sp3 to sp2, the JH changes from, you can see now it increases, as I told you, because S character is increasing, so it means increasing. Okay, that is I told you now. This was, and this is the that I have already told you. In case of cyclopropane has intermediate value, okay, minus 4.3 Hz, because due to more S character in CH bonds. If you see the cyclopropane has got banana bonds, the carbon-carbon bonds are having P character. So you will see they will be about sp4 type or something, whereas your carbon-hydrogen bond will be, let us say, sp2.5. Okay, it is, I am not telling that. So that means there is a more S structure in the carbon-hydrogen bond than the carbon-carbon bond in case of cyclopropane. Okay, that these values will be different. Okay, this I am just telling you relatively that all the orbitals or the MOs are not of same character. Okay, so that's why you see that and also they have the valency bond angle. So that's why you are getting this. And you can see the cyclobutane, it is increasing, and some other cyclic compounds also I have told you about. Okay, now let us see what is the effect of a substituent on two-bond coupling constant. Okay, so if you put an electronegative substituent, okay, like methylene group, okay, you will see a positive change in J value. Okay, that means absolute value decreases. Okay, so see methane, it was minus 12.4. Okay, it has indirectly measured. Now, if you put a chlorine group, you see this, the coupling constant of these two hydrogens. Now it has increased. Okay, the absolute value is decreased. Okay, but then that means it is an increase. It is going towards the positive side. It is increasing. CH2Cl2 it is increasing. But if you put an electronegative substituent at the beta position, okay, it makes a negative change. That means there will be an increase. Okay, like that. You see that case of ethylene, the value was 2.5, and I also explain why it is 2.5, why not minus, because of the sp2 character and the bond angle. Now you put a halogen here, you see that it is now changing the chemical shift value of the coupling constant value of this hydrogen, because it is at the beta position. Okay, so that is now becoming negative. It was plus to minus, and you put a fluorine. Fluorine is more, it is becoming minus 3.2. But if you put a electropositive lithium, you see it has now become more positive. Okay, so negative substituent. So alpha position, it has a positive change. In beta position, it has a negative change on electronegativity. Okay, and adjacent pi bonds causes a negative change, means value increases. Okay, so you can see here. So acetonitrile is only one pi bond, that is minus 16.9. But if you put as malonitrile, there are two pi bonds. See, now that has become more negative. Okay. Okay, you can see this in case of toluene. Okay, this toluene methyl. Okay, so it was minus 12.4, it has now become minus 14.5. Okay, similarly you can see these are the examples you can see, and these are self-explanatory. Okay, now for three-bond coupling constant, we call them vicinal coupling constant. And as with one bond, so 3J is expected to be positive. You can draw a scheme I showed for one bond, two bond. So you can draw yourself for a three bond. And if you are not able to do it, you can ask me later on. Okay. The magnitude of 3J depends on 4 factors. So in case of 3J, there will be three intervening bonds. So there will be automatically, you will see there will be a dihedral angle between CH bonds. Okay. And you know, this is the dihedral angle. Okay, so it is the plane of this hydrogen and this hydrogen. So it is the, I'll show you, you can see the, if you consider the, so let us say for ethane, okay. So this is the dihedral angle, Okay, so the diagonal angle is not a fixed angle because there is a free rotation about the carbon-carbon single bond. Okay, so the diagonal angle changes. Okay, but in case of alkenes, this is more or less fixed. Okay, but for saturated compounds, this dihedral angle is variable. So that depends on, you will see in that even the dihedral angle is variable, but you will see that the particular conformation is more favored over the other conformations. Depending on the substituent and depending on the stereo and electronic parameters. Okay. This carbon bond length, the carbon and carbon. What is the bond length? If the length is more, that will affect. I will see how this affects. And this valence angle, the angle between this and this bond, this is called the theta, or we can call this side as theta dash. Okay. So these are called the valence angle. Okay. And the electronegativity, and let us say you have a fluorine here, or you have a lithium here. Okay. So the electronegativity of the substituent, okay, are on the HCH moiety, HCCH moiety. Okay. So here I have explained you what is dihedral angle clearly, what is the bond length. I have already told you all these things. I have told, and I have told you this is the most of, this is called the stagger conformation when the phi is 180 degree. This is called the eclipsed conformation when phi is 0, and it is called the ghost conformation when phi is 60 degree. Now 3-bond coupling constant, the magnitude is a function of, say I am talking about the magnitude. Okay, sign, so I have already told you it will be positive. Magnitude of 3, or it is called the vicinal coupling, is a function of dihedral angle in addition to the gyromagnetic ratio of the interacting nuclei and s orbital contribution. Okay, that already I have told you that is most important thing. And that in case of this vicinal coupling constant, it is governed by one equation called Karplus equation. So Karplus has found that empirically found that he can correlate the coupling constant and the dihedral angle, and the equation is summarized here. In many books you will see there will be written A and B. Okay, but what he has found that A and B, A is almost most of the cases A is 7, or it is considered as a 7, B is 5. So 3JHH is equal to 7 minus cos pi. Phi is nothing but the dihedral angle plus 5 cos square phi hertz. Okay. So J reaches a maximum value. So if you put that when phi is equal to 0 is 11 hertz and phi is equal to and when phi is 180 degree, it is 13 hertz, and a minimum value when phi is equal to 90 degree. So that you can see here, this is for the phi is equal to 0, the eclipse conformation. This is the ghost conformation, and that value is minimum. That is around 2 hertz. And if you see when it is 180 degree, it becomes around 13 hertz. Okay, so this is your this is so how this J value depends on the. So this is a very useful thing for specifically to find out the relative stereochemistry. Okay, in many molecules, you will see that a particular conformation is favored, and see, although there will be contributions from other, you must remember that any molecule is not, until unless it is a cyclic system, there is a free rotation available for that, and there will be a distribution of conformations. Okay, so out of that, one will be more favored. Okay, so we are considering that only. Okay, so you get a weightage average of the coupling constant from all conformations, what you see in NMR. Okay, it is not that we are drawing the eclipse conformation means the molecule is in the eclipse. It is not like that. It is, there are infinite conformations possible. Okay, and each of them are having a coupling constant value, and you get a weighted average value of that which you see in your NMR spectra. So that's why you are getting 13 hertz doesn't mean you may not get 13 hertz. Okay, you may get 11.5 hertz, or you may get 8 hertz. Okay. So now then let us see why this angular dependence. So this is due to the stereoelectronic interaction between the two vicinal molecular orbitals. Now let's say when it is eclipsed, these two molecular orbital is interacting, so there is a good communication between the HA and HB. Here also the back lobes of these two, this back lobe is here and the other back lobe is there. So they are interacting strongly, and you are getting a strong coupling influence between this hydrogen and this hydrogen. But when they are in ghost conformation, there the interaction with the back lobe as well as the main lobe are very minimal. Okay, so the interaction between this hydrogen and this hydrogen is minimum, or the nuclei interaction is minimum. That's why at 90 degree this is nearly zero, or it is around 2 hertz, where you get maximum at 90 degree, and phi is when the phi is 0 degree and 180 degree, and a minimum when it is 90 degree. So that only I have told you, conformational distribution and conformations are changing rapidly. The 3HH averages out, and the observed value is the weighted average over all conformations. Conformational choice depends on temperature. You know it. The conformation ratio of various conformations can change with temperature. That's why 3HH is also depends on temperature. So if you are recording a NMR at, let us say, room temperature, and you are now recording the NMR at -70, okay, you will see there is a change in the coupling constant. The reason is that a change in the conformational preferences. Now, vicinal coupling constant in across double bond also with stereochemistry. Okay. So double bond does not allow rotation. So you have only two phi values. One is the cis 0 or trans 180 degree. Okay, and also you have the extra pi electron of the double bond, so they also help in communication. That's why you will see that there is about 20% more coupling constant value in case of double bond. That's why the J cis about 10 to 12 hertz. Okay, if you see that in saturated it was 11 hertz, but if you in trans it is 15 to 18 hertz, it was 13 hertz. Okay, so see there is a increase because of the pi bond is now making a better communication between the two nuclei. It is not only the lobes, also pi bonds. Okay, so there is a general formula or trends has been observed, like your calculus equation, that in unsaturated compounds the vicinal coupling constant depends on the bond length. I also told you that it depends on bond length. Okay, so that equation is that how it is related to bond length. It is minus 351 R plus 56.65 hertz. Okay, so now I'll give you one example like benzene. The benzene is having a longer bond, okay, longer pi bond than cyclohexene. So you can cyclohexene, this is your cyclohexene pi bond, and the benzene, okay, because of resonance, the bond length of all these bonds gets means all these bonds are having slight single bond character and slight double bond character, so you get a average value. That's why the bond length of pi bond length of this thing in benzene is greater than pi in cyclohexene. Okay, and that is clearly visible in their coupling constant. Okay, now if you see that we have seen the cyclic system, because it is a cyclic system and you have a double bond, this is a planar, so the phi, the dihedral angle is always 0. Okay, now but if you see this angle, this theta and theta dash, it depends on the ring size. So if you see that theta and theta dash decreases as you increase the size of the ring. So theta and theta dash decreases as increase in ring size. You can see very clearly, and see there is an increase in coupling constant, clearly seen. Okay, up to I have shown up to 8-member ring. It is now around 10 to 13 hertz, and now after that it is more or less remain constant. You see benzene, because of this theta is different. Okay, it is 7.5. Here, if you see, this is a 7-member aromatic. It is 10.3. When it is a 5-member aromatic, it is 4.0. Okay, so as the ring size is increasing, the coupling constant is increasing. So it is inversely proportional to the theta and or theta dash. Okay, so 3J values in saturated and unsaturated system decrease with increase in electronegativity of a substituent. Okay, so there is let us say okay, so let us say you have a compound CH2 CH3 CH2 lithium. Okay, there the coupling constant value is 8.9, but now if you are increasing the electronegativity, the J value decreases. You see lithium to silicon is intermediary, and then now these are cyano, chloro, ethoxy and OR2. You can see the clear difference between the O ethyl and OR2, because now this has become much more electronegative because of the OR2 plus it is. Okay, so the J value decreases. So as the electronegativity increases, the J value decreases. Same thing is true also in case of alkenes. And if you see, and there is a good relation is given, the J trans. So this, see, in case of saturated compounds, so 3J is 9.41 minus 0.8 into delta E. Delta E is the electronegativity difference between the substituent and the electronegativity of hydrogen. So if you know the difference, you can calculate. Similarly, for substituted ethylene, that value is, for trans, it is 19.0 minus 3.3 delta E. And for JCs, it is 11.7 minus 4.7 delta. These are all empirically found out. People have analyzed many compounds, and these are the empirical relations. Okay, and you can see here also, if you put a electropositive, you see the coupling constant. The JC's coupling is now almost 20 hertz. Trans is almost 24 hertz. Now, as you can go from see, now silicon, it is 14.7, 20.4. For alkyl, it is 10 and 16 point. Now, if you put halogens, you see that now they have decreased. Okay, so chlorine, it is now 7.3 Cs, trans is 14.4, fluorine is 4.7 and 12.8. Okay, so these value is like if you have hydrogen cis compound. Okay, so electronegativity has a, and same thing is for, if you see the in case of pyridine, you see this nitrogen electronegativity effect is making a lot of difference. Okay, you can see the coupling constant between these two protons and these two protons. Whereas aromatic, it is 7.5 benzene. But in this case, these two orthoprotons coupling constant is 4.88, but these two protons, it is 7.63. It is nothing but the electronegativity effect of nitrogen. Okay, so okay, I'll just finish in 2 minutes. Okay, now there is another class of compound like acetylene compound. So the 3JHH is low, around 9 hertz. See, you may think that acetylene is having more S character, more pi electron density. Why the value is low? Okay, the reason is that the CH-MOs are collinear. So there is a very little overlap between the MOs, okay, because they are in the same line, okay, and they face opposite direction, hence they interact very poorly. Okay, again, for you will see in case of cyclohexane, you will see the JAA, the axial coupling constant is always more than axial equatorial, and that is equal to JEE. That actually helps in finding out the stereochemistry in cyclohexane containing compounds. It's very important. In case of cyclopropane, this J6 is greater than J trans. Okay, so cis, the phi is equal to 0, where trans it is 130. See, if you see that cyclopropane, you know the bond angle, I told you this hydrogen and this hydrogen, this is 115 degree. Okay, so similarly, if you see that this hydrogen and let us say you have a substituent here, you will see that the dihedral angle between these is phi is equal to 0. Okay, Similarly, automatically, when they are trans, they will be 130. It will not be 180, it will be 130. Okay. And we know that when the phi is 0, it is 11. And when phi is 180, it is 30. So 130 will be less than that. Okay. So that's why always just is. Okay. Now, long-range coupling, you can see that these, I have told you the long-range coupling, when you have a pi system, like benzene case of, you can get up to para coupling. Okay. Okay. That is because of the monkey girl. Okay, so these are the examples. These I've already told you, and you see the number of bonds, even up to 7 bonds you can see in case of C, because of the pi systems, conjugated pi systems. So you can see the coupling constants more beyond that. These are very special cases that I have already explained to you. Okay. Another type of very important that you can see, this is my last slide. Okay, so when the long range coupling, you can see up to 4 bond. Okay, this is very interesting in stereochemistry analysis. Okay, specifically to see, this is known as a W coupling. Okay, so if you have a equatorial group here, you have a equatorial here, so JEE, so they have a W type conformation, and you get a coupling constant, and it's clearly seen in molecules. So if you have, so how, if you have two substituents, let us say, are arranged in axially, so you will have two equatorial protons. Okay, although they are 4 bond away. Okay, but still, now why this is happening? Because if you see, when they are in a W type conformation, you see these back lobes, they interact. This is nothing becoming like a 1 bond, 2 bond, and 3 bond. So this is becoming a system like a 3 bond, although there are 4 bonds. So that's why this W coupling is very useful in stereochemical analysis, specifically cyclic system. And you see in this particular case also, you have this W coupling. Okay, the blue hydrogens, this bond should also be blue. And you see in this case, this is a very strong W coupling. J is equal to 7 Hertz. In this case, it is near 2 Hertz. This is 1 Hertz, but this is 7 Hertz. Okay. So see here, there is no interaction of the nuclear through the pi system. Here simply through sigma system, but here the sigma bonds are arranged in such a way that the back lobes are now communicating. Okay, so it is actually reducing the distance between the interacting nuclei. I think I'll stop here. So if you have any questions, discuss. Okay. So if you have any question, you can ask me.
By mistake.
Okay, it's fine. So if you have any question, okay, and today your assignment will be posted, and you have to submit it by 17th of March, means you have now 2 weeks time, by 17th of March, 6 p.m. So before that, so what you do, you have to solve it, scan it, and send it through the email. Okay. And your will accept till 6 p.m. 17th March. Okay, you must remember that all these assignments will carry some marks final. Okay, in your final assessment. Okay, so that we have not yet decided, but certainly there it will carry a good amount of weightage. Okay, so please solve it, so that, and if you have any doubt in between also, you can ask me. Except you cannot ask me the answer of the questions, but I can tell you if you have any doubt about your concepts or understanding, individually or collectively. Okay. Any doubt, you can tell me, or you can also give some feedback whether I am going too fast or too slow. I cannot be too slow, because I have to cover a lot of things. Okay. There are many things, but if you understand, these are the minimum things, and certain things you can explain logically if you understand this. Okay. Okay, then we'll close here. Then we'll meet again on Monday at 4 p.m. Okay. So please remember, Monday at 4 p.m.